Hello, this is Tyler Beamer, math instructor, Haywood Community College. This is an instructional math video for Math 272-01. This video is surrounding the topic of length of curves, and this is from our text, Chapter 6, Section 5. So we've actually already derived this integral formula for arc length, which is how to find the length of a portion of a curve for a function. So I'm not going to do that again just for the sake of time. That derivation, if you want to look at that again, is on page 445 and 446. But the integral formula is on page 447, and that's what we're going to use in these following examples. But the arc length can be found on an interval from A to B, and these are our x coordinates for our interval. For arc length, and we want to take the integral of the square root of 1 plus f prime, which is the derivative of our function, squared. Okay, so let's start by doing number 9 on page 450. This is a linear equation, so we really wouldn't necessarily have to use integration to find the length of that section, since it's a straight line and it's not curved. But since it's a calculus class, we will use calculus here. It'll be a good beginning problem. Here's our interval, -2 to 6. So this is our A and B. Those A and B points are going to be x coordinates. It's going to be basically telling us the beginning and ending points for our curved partition. Okay, so and then we want to find the derivative of our function, so y prime, which in this case is -8. So now we can plug in our information to our interval. We've got A and B. We've got 1 plus -8 squared f prime is -8. So then we want to integrate this. So from here, we can, take care of what's inside this square root. So -8 squared is going to be 64, plus 1 is 65. So we're looking at integrating from 6 to -2 the square root of 65. So we're looking at a definite integral here. Okay, so then we want to integrate that. So we treat this almost just like it's a constant. So basically we are going to throw an x in there. So x times root 65, integrate that from 6 to -2. Okay, so that's going to look like this. Of course, those double negatives are going to turn to positives, and then we end up getting 8 times the square root of 65. So that would be the distance on this function from -2 to 6. Okay. All right. So that's an easy example to start out with. Okay. So let's look at one that's a little bit more challenging here. Okay. I'm gonna turn this paper over. All right. So let's look at number 13, and this is going to be on page 450 if you want to take a look at that in the book. So here's our function. And we're looking at this on the interval 0 to 1. So, sometimes it's kind of helpful to look at this graphically. So let's do that. I'm just going to plug this into our calculator. Try to get this glare off of here. Well, that didn't help either, did it? Sorry about that. Okay, so I'm going to put this in our calculator and see what we got as a graph. So x squared plus 2 to the 3/2 power over 3. And I'm going to graph that on the interval from 0 to 1 on the x-axis. So x min 0, x max 1. Alright, so see if you guys can see this. So I know that's dark, but basically we've got a curved line, right? It looks kind of straight, but it's not. It starts to curve up here at the end. So if we have a function that curves and we're looking at a piece of that curve to find the arc length or distance there, we would want to use calculus, right? We couldn't use straight up right triangle trig or some algebra distance formula or anything, because we're not dealing with straight lines in this case. Alright, so sometimes it's good to look at the function graphically just to get an idea of what exactly we're finding here. So I think on this problem it's helpful to rewrite this so that it looks like this. So basically I just took this 1/3, since it's got a 3 in the denominator, out in the front. And then I can find the derivative of that pretty easily by doing the chain rule. So I'm doing 3 over 2 times 1/3, which is going to give me 1/2. Keep this parentheses the same. Subtract 1 from the 3 over 2, which gives me 1/2. And then times that by the derivative of what's inside, which is 2x. Okay. So then that gives me my derivative. So I'm going to clean that up just a little bit, because I can multiply 1/2 and 2 there and just end up getting an x. So we end up getting this. Okay, so that looks a little better. Alright, so now let's put that in our integral. So there's my a and my b. So that's given to me. Square root of 1 plus f prime squared. So this whole thing squared. I don't want to forget our dx. Okay. Alright. So now at this point, we want to do some work here to clean this up just a little bit. Okay, so I want to essentially square this. So this is going to be x times root x squared plus 2. Okay, and then I'm going to essentially times it to itself, since it's getting squared. So it looks like this. So basically I just wrote the 1/2 power as square root. Okay. So then if I multiply those two things, right, together, right, then I should get x squared and then times these two guys together gives me the exact radicand of what's inside. So the square root of x squared plus 2 times the square root of x squared plus 2, that just gives me x squared plus 2. Okay, so I just multiplied the outside numbers, x and x squared, square root x squared plus 2 times square root x plus 2 gives me x squared plus 2. So then I can multiply these two guys and get x to the 4th plus 2x squared. Okay, and then I don't want to forget about the plus 1 that I have. Okay, and I don't want to also forget about this whole radical that's still there. Okay, Alright, so there's a good bit of algebra in some of these problems, so just don't forget about all of the fine details. Alright, so here's the trick with a lot of these problems is, this is going to be way easier for me to integrate if I can get rid of that square root. Okay, so obviously the inverse of square root would be squared. So if I could somehow rewrite this so that the inside is something squared, then that square root and the squared will cancel, and then that's going to make it way easier for me to integrate. So keep that in mind when you're doing these problems. That's kind of a common theme. Alright, so I'm going to write this so it's in standard form, which might make it a little bit easier for me to see the integration. So I see I've got a 1 and a x to the 4th, so automatically I'm thinking x squared plus 1 times x squared plus 1. Obviously I want the factors to be exactly the same, so I can then get something to the second power. So I check myself. If I do FOIL on that, right, I get x to the 4th plus x squared plus 1. So I do indeed get x to the 4th plus 2x squared plus 1. So that's just a checking mechanism. So check, we're good. Okay, so I have factored that correctly. Okay, so I'm going to move this up a little bit. So now I can rewrite this as x squared plus 1 squared. And then now that square root and the square are going to cancel. And I get the integral of x squared plus 1 dx. And then of course this is way easier for me to integrate because now I can just use the power rule. Alright, so using the power rule, I get 1/3 x to the 3rd plus x going from 1 to 0, and that's going to give me 4/3. Okay, so then that would be the distance. Once again, going back to the graphical representation of this. You guys can see it a little better if I move it up here. Perfect. There we go. So that's the distance of this curve, right? I know that looks like it's kind of straight, but it does curve slightly. So think about taking a tape measure, right, a flexible tape measure, and running it from 0 to 1 along this curve. That's the distance there. Okay. All right. Okay. So I've picked examples that are similar to the types of problems that are going to be on your homework. So hopefully these will be a good guide for you. So let's look at number 12. And this is on page 450 as well. So if you want to follow in the book here. So here's our function. It's on 1 to 6. So once again, I think it's helpful to look at this graphically, especially when you're first learning this, so you can kind of get an idea of exactly what you're doing. I mean, we can blindly follow the definition in the book, but we also want to have a good conceptual understanding of the process here. Alright, so there we go. So there's our function, 3 ln of x minus x squared over 24, and that's on the interval from 1 to 6. So like I said, think about taking a flexible tape measure, starting here, measuring from here to here, 1 to 6. What's that distance, right? We're finding the measurement of that arc length. That's what we're doing through this calculus. Alright, so let's find the derivative. Okay, so remember that the derivative of ln of x is 1 over x, and so you want to probably still use the table of derivatives that I gave you in Calc 1, which is also on Moodle, but it's kind of been a while since we've done a lot of derivatives. We've been in integrals here for a while, so this piece of paper will be helpful to find those derivatives. And so the derivative of the 1 over, or ln of x is down here. Okay, so ln of x is 1 over x. Okay, so just keep that in mind. That's a helpful reference. All right, and 3 is the constant multiple, so that just gets multiplied there, and then we're using the power rule, right? If you basically think of this as being 1 over 24x squared. Oops, can you see that? That might be helpful. So then you're doing 2 times 1/24, which is 1/12, and then subtracting 1 from the exponent. So that might be helpful to think about it like that. Alright, so then we want to find arc length from 1 to 6. Square root of 1 plus 3 over x minus x over 12 squared dx. Alright, so essentially square this out. So 3 over x minus x over 12 times 3 over x minus x over 12, expand that using a FOIL or whatever you do there. And so that's going to give you 9 over x squared minus 1/2 plus x squared over 144. And then of course don't forget to add the 1 that's still there, and then that's all under the square root still. Alright, so that's how our integral is shaping up. Now 1 and minus 1/2, obviously those are like terms, so I can combine those to give me 1/2 plus 9 over x squared plus x squared over 144. Okay. And that's all under our square root. Okay. So from here, right, we want to keep in mind that we want to try to somehow factor this or do something to get rid of that radical. Okay, so actually, since we have all fractions right here, what I did is tried to just add all the fractions up and just basically see what happens. Okay, so part of this will be experimental, some trial and error. But, like I said, the long range goal is to just try to get rid of that square root. That'll make it way easy to integrate. So the GCF here would be 144x squared for all 3 of those fractions. So if I rewrite this so that they all have a common denominator, right, I multiplied this by top and bottom by 72x squared. I multiplied the top and bottom here by 144. And then I multiplied the top and bottom here by x squared. So that gives me a common denominator, and then I can add all of those up, put that under one single fraction. Like so. Okay. And I know that if I have a fraction under a square root, I can break that up and take the square root of the top and the square root of the bottom. The bottom is really nice. That's a perfect square number. 12x would be the square root of the denominator, but I need to somehow factor that numerator so that I can get it as a factor squared, so identical factors there. And so that works out really nicely, right? I see 1,296 and 72, so I'm thinking 36 times 36 is 1,296, and 36 plus 36 is 72. So that works out pretty nice. That's an x to the fourth. So I'm going to rewrite this as this on the top. Here's my bottom. So obviously I can rewrite the top as this. And that's all under the square root, and I can break that square root up into the top and the bottom here. So then that's going to give me x squared plus 36 over 12x. Okay, so that gets rid of my square root. Now I still haven't taken the integral of that. Okay, so I think we should split this up. That'll make it easier to integrate. So basically we have 1/12 x plus 3 over x and then we want to integrate that. Okay, so let me turn to the other side of the paper here. Alright, so we're looking at this. Essentially, so we can essentially take the integral separately there. So 1/12 gets pulled out, 3 gets pulled out. So we get that. We can use the power rule here. So I get 1/12 times 1/2 x squared when I integrate. And then remember that the integral of 1 over x is ln of x. So 3 times the ln of x, and then of course I can multiply those two fractions. It's 3 ln of x. So that's my integral, and then I want to do that from 6 to 1. Okay. So then we can put our 6 in here. And for x, put our 1 in here for x. Okay. And then we want to simplify, right? So this is actually going to give us 3 over 2 when I do the math on that. This obviously is going to stay 1/24. Alright, so then let's combine some like terms, right? So 3 over 2 minus 1/24 is going to be 35 over 24. Okay, ln of 1 is 0. So this whole thing basically just goes to 0. That's going to cancel out. Okay. And so we're left with 35 over 24 plus 3 ln of 6. And of course that's going to be our exact answer for that particular problem. Alright. So there's definitely some multiple parts to these problems. Pay attention to all the fine details, right? There's a lot of algebra in the intermediate steps, and of course that could cause some problems if you do something out of order or incorrectly. Alright, let's do another one here. I'm going to give you guys plenty of examples. That way when you get to your homework, you see one similar, you can go back to the video and use it as a reference, hopefully. So, alright. So there's our curve. There is our function. So it might be easier to rewrite the function if we distribute that 1/2 through. So that our function looks like that. And so then we want to take the derivative, and of course the derivative of e to the x is e to the x. Obviously we've got a coefficient here. We want to use that ke to the kx formula. So that -1 is going to come down here. So we get -1/2 e to the -x as our prime. Okay, so this one's turning out to be a doozy. We got a ln of 2, -ln of 2 as our intervals. One plus, and then we want to square our derivative that we just found under the radical. Okay, so then we want to square this, right? So multiplying it times itself, expanding it using FOIL, however you want to think about that. So just write all this out here for you just in case you need it. It's a -x. Okay, so then we end up getting 1/4 e to the 2x minus 1/4 e to the 0 minus 1/4 e to the 0 plus 1/4 e to the -2x. And of course, e to the 0 power is 1, so that's basically -1/4 minus 1/4. So that ends up being -1/2 there. When I combine those two together, and then 1 minus 1/2 is going to give me 1/2, since these are going to be like terms. So and that's all going under the square root. And of course I haven't integrated anything yet. We're just cleaning it all up. So there's a lot of algebra in there. That's what you got to be careful of. Okay, so now we want to somehow factor this, right? So that we get something squared, right? So we can get rid of that square root, and this may be trial and error. But I see that I've got some 1/2 and a 1/4. I know 1/2 times 1/2 is a 1/4. I've got some e to the x's, e to the -2x. I'm thinking, well, e to the -x times e to the negative x would be e to the negative 2x. So let's try this. 1/2 e to the x plus 1/2 e to the negative x squared. So basically it's multiplied times itself. And this part may be a little bit of trial and error, just to try to get something that's going to work. So if I expand all of that out, I'm going to get 1/4 e to the 2x plus 1/4 e to the 0, and I know that e to the 0 once again is going to be equal to 1. Anything to the 0 power is equal to 1. Okay. So let's see what happens. Is that going to give me what I had initially? It does, right? So this is all just essentially a checking mechanism, and yes, we get here what we have up here, and that was our goal, right? So this is all just checking, making sure that I have the right factors, essentially. Alright, so now I can rewrite this as 1/2 e to the x plus 1/2 e to the negative x squared, and that's all under the square root. And now that works out nicely because the square root and the square will cancel. Alright. And of course, that makes the derivative a lot easier to find. Or not the derivative, the integral, sorry. The integral a lot easier to find. Okay. So we want to integrate, and of course the integral of e to the x is, once again, e to the x. So that makes it nice. The integration's easy. Remember, we're going to divide this coefficient by the coefficient of our exponent here, so that negative 1's going to come out front, and that's going to be a definite integral here, ln of 2 to negative ln of 2. So then we want to rewrite all of that. So 1/2 e to the ln of 2 minus 1/2 e to the negative ln of 2 minus 1/2 e to the negative ln of 2 minus 1/2 e to the ln of 2, since those two negatives will make a positive there. So I'm just plugging in my definite integrals here, and doing some math here, some arithmetic to clean this up. So we know e and ln are going to cancel, so this is basically going to give me 2, and 2 times 1/2 is 1. Okay, this, since that's a negative exponent, is going to be written under 1, so that's this. And we've done this in some other problems. This is the same as 1 over e to the ln of 2. Right? So that's basically a half, and a half times a half is a fourth. Same thing here. That's going to be a fourth. And same thing here. That's going to be a 1. So 1 minus a quarter is 3/4. Minus a quarter minus 1's negative 3/4. And of course those double negatives are going to turn to positives. So that's really going to be addition, which will then turn to 3 over 2. Alright. So that's yeah, quite a bit of work there for that one particular problem. But as the theme for a lot of these problems, the calculus isn't too bad. It's just all of the intermediate algebra steps and the factoring, Just be very careful there. Pay attention to detail. All right. So as with a theme here for our other sections, once we figure out how to integrate in regards to x, now we're doing it in regards to y. So here's our arc length for x equals g of y. Alright, so those a's and b's are going to change to c and d, and of course those are going to be our starting and stopping points in regards to the y coordinate. Okay. Square root of 1 plus g prime, so I need to solve my function for x and then take its derivative. Okay. So here's 28. 28 says find the arc length given this information. So for this function, notice it's solved for y. It's going on the interval from 1 to 2, or 1 to square root of 2 on the x-axis. Now, I mean, you could obviously just do this problem like we just did the other ones. I guess certain situations it may be easier to do this if it's solved for x, because it might be easier to derive or integrate. I didn't do this one solve for y since the directions told me otherwise. This is number 28, sorry, on page 450. So I didn't do it that way, so I can't compare, but we'll do it this way just to show you. So, all right, first things first, solve this for x, and this can be a little bit tricky. I mean, if I did both ways correctly, I should get the same distance, so it shouldn't really matter. But remember, ln is log base e. So I can rewrite this in exponential form, e to the y equals x minus root x squared minus 1. Then I subtracted that x on over. Divided everything by negative 1. Okay. And then I squared both sides. So basically, when I squared this, I have to expand that, which is going to end up being e to the 2y minus 2x e to the y plus x squared equals x squared minus 1. And those x squareds can essentially just get subtracted from both sides. So I get this. I can factor out a e to the y, since they have that both in common. Divide by e to the y. Subtract the e to the y. So I'm basically just trying to isolate x here. That's my thought process. And then I want to get rid of the negative 2, so I can times by negative 1/2. That might be the best way to think about it. Times by negative 1/2, and so I'm going to get this. And now it's solved for x. We can clean that up a little bit. you know, if I bring this up to the top, that gives it a common denominator, and then I can add it pretty easily from there. So that's quite a bit of work just to get it solved for x. Okay, so that's really the first step. And then the next step is, well, I've got to figure out what my c and my d are, right? So if I go back to my initial problem, this is actually a and b. That's in terms of x. I need c and d, which is in regards to y. So I'm just going to plug each of those into my function. Well, I don't know why I wrote a x there. So I'm going to plug 1 in there for x. Into my function, and so that gives me 0, and then I'm going to plug in root 2 alright, do some algebra there, and I get ln root 2 minus 1. So this is my c and my d, right? So here's my c, here's my d. So we've got to rewrite those so that they're solved for y. Basically, you know, where is that curve on the y-axis, not the x-axis, right? Okay, so now we can do some integration. So I'm going to well, before we do integration, all right, let's find the derivative. We didn't do that part. So let's go back to our function here at solve for x. I'm just going to rewrite this so that it looks like this. So now it might be easy to find x prime. Okay, using my KEKX rule. Alright, so now we've got c and d, we've got our function solve for x, we've got x prime, so now we can do our integral. This is a lengthy problem. Alright, so here's what our integral is going to look like for the length. Okay, so I've got 0 ln square root of 2 minus 1. Okay, square root of 1 plus negative 1/2 e to the negative y plus 1/2 e to the y squared dx. Alright, so let's square this guy, right? Let's do all that. You know, basically expand that with FOIL, whatnot. So we should end up getting 1 plus e to the negative 2y over 4 plus e to the 2y over 4 minus a half. Okay. Well, this is what we get when we square it, this part. Obviously that 1's already there. Okay. Okay, so now we can combine the 1 and the minus a half to get 1/2 plus 1/4 e to the negative 2y plus 1/4 e to the 2y. And then I want to somehow rewrite that so that it's something squared. So I've got a half, some quarters, right? So half times half is a quarter. E to the 2y, so that's got me thinking e to the y times e to the y is 2y, e to the negative y times e to the negative y is e to the negative 2y, right? So you just need to play around with that, come up with those factors, and we end up getting this. Right. So just like the common theme in the other problems, right? We want to factor this so we get something squared. So they're identical factors. And so that allows that square root to go away, which that makes it really nice, because then it's easier for us to integrate. Okay. Alright, and so then we want to integrate from here. So do our integral. Do our definite integral. Right, and then all of that should equal 1. Right, so when we plug those in, e to the 0 is going to give us 1, and subtract it with the ln. The ln and e's are going to cancel there. You should be able to work that out and get 1. Alright, so hopefully this gives you enough instruction for being able to find the length of curves. If you have any questions, please email. And I will see you guys next Monday. Alright, stay warm.